Hi, welcome to the next video. So we're going to continue where we left off. So at the end of the last video, I gave you the volume using the cylindrical shell method. So the V is equal to def integral from A to B of 2 pi x f of x dx, where 0 is less than or equal to A, strictly less than B. Right, that's the volume. How to calculate the volume of a rotated region using cylindrical shells. Okay, and here S, here capital S is the solid obtained by rotating about the y-axis, the region bounded by y equals f of x, y equals 0, x equals a, and x equals b, where b is greater than a, greater equal to 0. Capital V is the volume of that solid, right? And so an example, a picture I drew of this happening, if this is the x-axis and this is the y-axis, and you have a graph like this, y equals 2x squared minus x cubed, and you have the line x equals a and line x equals b, and you have the y equals 0, the x-axis, and okay, so then the region bounded by those four graphs, y equals 2x squared minus x cubed, x equals a, x equals b, and y equals 0, and you see the region between them. So then the region between all those curves, y equals 2x squared minus x cubed, x equals a, x equals b, and y equals 0. If you rotate that about the y-axis, then right here b is greater than a, greater equal to 0, and so if you rotate this about the y-axis, okay, so then you get that rotated region, right? And so the volume at the top, that def integral, calculates the volume of a region like that. Okay, so that's what we did at the end of the last lesson. Okay, so now in this lesson, we're going to do a few examples, and we're going to calculate volumes using that formula, using that equation, which will have to do with problems like this. Okay, so let's look at the first example. And so actually in the first example, it's going to be this picture we can use in the first example we're going to do. So example, find the volume of the solid obtained by rotating about the y-axis the region bounded by y equals 2x squared minus x cubed and y equals 0. So example, find the volume of the solid obtained by rotating about the y-axis the region bounded by y equals 2x squared minus x cubed and y equals 0. Okay, so in this example, this I illustrated if it was bounded between x equals a and x equals b, right? Here the x equals a and x equals b are going to So I guess I'll keep the pictures of those cylindrical shells, but we're actually going to take the entire region below the curve, including, so we're going from 0 to this point. We're going from here to here, and we're rotating the whole thing around. So we're getting this entire rotated region, not just up to here, but all the way up to there. Okay? That's bounded by y equals 2x squared minus x cubed, and y equals 0. Okay, so we need to know the coordinates of the points where this curve crosses the x-axis. So the coordinates here is the origin. Our origin is obviously 0, 0. And what is the x-coordinate of that point? So we just need to find where this graph crosses the x-axis there. So if you let 2x squared minus, let me write solution here. Okay, so for the solution, if we have 2x squared minus x cubed equals 0, and I factor out the greatest common factor of x squared, I get x squared times 2 minus x equals 0. That means either x equals 0, because x squared is 0, or x equals 2, from 2 minus x is 0. So that means the x coordinate at this point is 2. So the coordinates here are 2, 0. Okay? Now, if we do a cylindrical shell, right, we could use a shell like this one here, right? So let's look at this cylindrical shell. Okay? So the volume is going to be by our formula, the definite integral from x equals 0 to x equals 2 of 2 pi x f of x dx. From our formula that I mentioned already before using cylindrical shells. Here f of x is just here f of x is just 2x squared minus x cubed. And so we just substitute 2x squared minus x cubed for f of x is equal to definite integral from 0 to 2 of 2 pi x 2x squared minus x cubed dx. Okay, so that's f of x here. And so this is equal to definite integral from 0 to 2. I'm going to move the 2 pi outside of the integral sign. And 2 pi times definite integral from 0 to 2 of x times 2x squared minus x cubed, which is 2x cubed minus x to the 4th dx. Okay. So then we take an antiderivative of the integrand functions, and then x to the 4th over 2 minus x to the 5th over 5 is an antiderivative of that integrand function. Okay, so an antiderivative of 2x cubed is 2x to the 4th over 4, which is x to the 4th over 2. And an antiderivative of x to the 4th is x to the 5th over 5. So that minus that antiderivative is x to the 4th over 2 minus x to the 5th over 5, evaluate from the lower limit 0 to the upper limit 2. Okay. So that's the picture. So that's how we got this. Let's see if I can do this without getting rid of the picture. That's equal to 2 pi times, I'm going to plug in 2 to the 4th over 2 minus 2 to the 5th over 5. That quantity minus the quantity 0 to the 4th over 2 minus 0 to the 5th over 5. So then this is equal to 2 pi times 2 to the 4th over 2, which is 8. 8 minus 2 to the 5th over 5, which is 8 minus 32 over 5. And that's 8 minus 6 and 2/5. And so that's 1 and 3/5. So that's 8/5. Okay. And so 2 pi times 8/5 is equal to 16/5 pi. That's the final answer. And that's the answer. The proof is done. And the picture is here. Okay, so that's our first example of using cylindrical shells to find the volume of a rotated region. So I'll leave this up for a moment so you can copy stuff down. Okay, so let's take this. Okay, so now that example is done, another example. Find the volume of the solid obtained by rotating about the x-axis. Sorry, about the y-axis. Rotating about the y-axis. The region between y equals x and y equals x. Okay, so next example, find the volume of the solid obtained by rotating about the y-axis, the region between y equals x and y equals x squared. Okay, so we're going to find the volume of the solid obtained by rotating about the y-axis, the region between Okay, so that's y equals x and y equals x squared. Okay, so those are the two graphs. Okay, so now so the region between them is that. So we'll rotate this about the y-axis. Okay, so we have a washer, and so we're going to find the volume. So we take the volume, and that's equal to definite 0.0, and then here the intersection point is 1, 1. Oh, right. Before we were using the washer method. Now we're going to use the cylindrical shell method. Good. Okay, so we have the cylindrical shell there, so let's find the volume. So the volume is defined from 0 to 1, 2 pi x, but now here, instead of f of x is going to be the difference of two functions. So I'm going to call it f of x minus g of x dx, okay? Where f of x is the upper function and g of x is the lower function. So this is going to be y equals, so this is the upper function. So I'm going to say this is y equals f of x equals x. It's the upper function. And the lower function is here. So I'm going to say y equals g of x equals x squared. Okay? So f of x is the upper function, g of x is the lower function. The difference in the values of f and g is the height of the cylindrical shell. And so 2 pi x is the circumference, and the height is f of x minus g of x, and then all dx. And so f of x is here, x, g of x is x squared. It's equal to definite from 0 to 1 of 2 pi x times f of x, which is x, minus g of x, which is x squared. Dx is equal to 2 pi from 0 to 1 x squared minus x cubed dx. Okay, so now 2 pi times the antiderivative of x squared minus x cubed is x cubed over 3 minus x to the 4th over 4, evaluated from 0 to 1. And so then that equals 2 pi times, plugging in 1, you get 1 cubed over 3 minus 1 to the 4th over 4, and minus 0 is just 0. So I can write that. So this is 1/3 minus 1/4, which is 4/12, minus 3/12, which is 1/12. 2 pi times 1/12 is pi over 6. So you calculate that, you get pi over 6, and that is the volume. Okay, so so you rotate that region about the y-axis, and you use cylindrical shells, and you get the answer is pi over 6. You just do 2 pi x, but instead of h being the height of a function, now the height is a difference of two functions, because now the height of the cylinder is, this height you can see is the difference in y values of two different functions. It's the is this y value, which equals x, minus this y value, which equals x squared. So the height is x minus x squared. All right, and so this problem we add one little thing to what we were doing before with cylindrical shells. Before, the height was the value of a function. Now the height of the cylindrical shell is the difference in values of two functions, and that's the only difference. Everything else is basically the same. Okay, and so that's now another example using cylindrical shells. So let's do a third example. Use cylindrical shells. Use cylindrical shells to find the volume of the solid. Use cylindrical shells to find the volume of the solid obtained by rotating about the x-axis, the region under the curve. Y equals the square root of x from 0 to 1. Okay, so example, use cylindrical shells to find the volume of the solid obtained by rotating about the x-axis, the region under the curve y equals square root of x from 0 to 1. Okay, so let's draw a picture of this region. So the x-axis, the y-axis, nice and easy so far. You have the graph of y equals the square root of x. Okay, you have x equals 0, and you have x equals 1. Okay. Okay, so that's the region under the curve of y equals the square root of x from x equals 0 to x equals 1. I'm going to rotate that about the x-axis. Okay, so I'm going to take this point, I'm going to rotate it about the x-axis. And so we'll see, we get that, see the mirror image. And so that's right, you have a picture of the three-dimensional object, the rotation of that shaded region about the x-axis. Okay, so we want to find the volume of it. And we're going to use cylindrical shells to do that. So to use the method of cylindrical shells, let's let's see how to, let's use these as our cylindrical shells. So the height is going to be the height is going to go from here to here. I'm going to rotate that line. So okay, so you see this line segment here, which is parallel to the x-axis. If you thought of starting at a point in this graph and going right to the vertical line, x equals 1, you could sweep over this entire shaded region by vertical lines, right, in such a way that if you kept taking these horizontal lines, you kept taking these horizontal lines, and you had them sweeping, up and covering the shaded region, you would cover the shaded region. Now, if you rotated each of those horizontal lines around the x-axis, all of them, you would then cover the entire three-dimensional object. And so we're going to take as our cylindrical shell, what happens if you take this horizontal line segment and you rotate it around the x-axis. And so you get an object like this. There's your cylindrical shell. Okay? And so that's one particular cylindrical shell. And so we can use that in order to find the volume. So the volume is definite integral. Now it's going to be with respect to y. And that's because if you look at the thickness of the cylindrical shell, the thickness will show you what variable you're using for the integral. The thickness here is a length. The length of the thickness is a difference in y values. And so your definite integral is going to be with respect to y. And the y values are ranging from 0. This is when x equals 1. So this point is 1 comma 1. When x is 1, y is 1. So the y values are ranging from 0 here, because this point is 0 comma 0. So the y values are ranging from 0 to 1. Second quarter, right? So y values are ranging from 0 to 1. And you have 2 pi y now. And so the reason why it's 2 pi y is because you look at the circumference of this circle, right? The radius of the circle is the height of a point on the graph, right? This point is coordinates x comma y. The height of the point is y, and that's the radius. So 2 pi y is the circumference, right? Before when we had 2 pi x, that was an integral with respect to x. Now it's with respect to y. And so our formula is going to be slightly different. And so the formula is going to be of the form v equals the definite integral from c to d of 2 pi y f of y dy. That will give you the volume when the cylindrical shells are in this direction. So now the cylindrical shells are facing that way. And when they're faced on the side, you use that formula, right? When the cylindrical shells are upright like that, you use the formula, this is upright, that's equal differential from a to b of 2 pi x f of x dx, right? So that's the formula for using cylindrical shells when the cylindrical shell is vertical. When it's horizontal like this, see this is horizontal, you're using that one, okay? You're integrating with respect to y. So since the cylindrical shell is facing this way, it's respect to y because the thickness of the cylindrical shell it gives you the dy. Here, the thickness of the cylindrical shell gives you a dx. Delta x, delta y, which corresponds to dy and dx, okay? I guess I'll write delta x here. The thickness is delta x, and the thickness here is delta y. But then when you integrate, you end up with a dy here and a dx there. Okay, so we have a 2 pi y f of y. F of y is technically the height of the cylindrical shell. But here, again, just like when you had, instead of f of x, we had f of x minus g of x, the height of the cylinder is now a difference of two functions. So in the place of f of y, and we already showed an example of this, instead of the height of a function, the height of the cylindrical shell could be the difference of heights of functions. And so here, the height of the cylindrical shell is going to be the entire length of 1. That's 1, because this is x equals 1 here. This is 1. And you can subtract this x distance. This x is on this graph. So you can think of y equals the square root of x, or you could say it's equal to y equal, or it's x equals y squared. So we're going to think of the graph of the equation y equals x squared as y equals the square root of x. Instead, we're going to think of it as the graph of x equals y squared. And so that means that this x distance here at this point is equal to y squared. So this is y squared, the whole thing is 1. And so the difference is 1 minus y squared. 1 minus y squared is the height of the function. So 1 minus y squared is the height of the function. Again, you want the height of the cylindrical shell, which is this. The height of the cylindrical shell is 1 minus the x coordinate of this point. So 1 minus the x coordinate of this point is 1 minus y squared. And so the v is equal to differential from 0 to 1 of 2 pi y times 1 minus y squared dy. And so when you compute that differential, you find the volume of the rotate region. Okay. So this is equal to 2 pi times the differential from 0 to 1 of y times 1 minus y squared is y minus y cubed dy. And this is equal to 2 pi times y squared over 2 minus y to the 4th over 4, evaluated from 0 to 1. And this is equal to 2 pi times plugging in 1, which is 1 squared over 2 minus 1 to the 4th over 4 minus 0. So I just get rid of the minus 0 part. And that's equal to 2 pi times 1/2 minus 1/4, which is 1/4. 2 pi times 1/4 is pi over 2. That's equal to pi over 2. Okay? And so here we use the cylindrical shell method. Earlier we used the washer method, and actually the washer method was easier. So we did the same example before and got the same answer, but the washer method here is easier. So the washer method for this example is easier. And so sometimes doing the harder technique gives you a more complicated answer. Okay, so here using cylindrical shells is more difficult than using washers, and the answer is more difficult. So sometimes though using cylindrical shells is necessary because cylindrical shells actually leads to a simpler answer than washers. But in this case, what looks like a simpler method is a simpler method for this problem. Okay, it depends on the problem. It's not a cut and dry thing like one method is always better than another method. You kind of have to think creatively and think which method is best for any particular example. Okay, so we have circles, we have washers, and we have cylindrical shells. We have 3 different shapes we can use to find volumes. Okay, circles, washers, cylindrical shells. Those are the 3 we've used. Okay, and there's a sort of an intersection between the washer method and cylindrical shell method. There's some problems you can do with both the washer method and the cylindrical shell method. But usually in those examples, there's one that's easier to do with one method than the other. And I might think that you'd probably want to use the washer method most of the time if you could use either one of the two. Okay? But there's a lot of problems where you can only use the washer method and not the cylindrical shell method. And there's a lot of problems you can use the cylindrical shell method, but you can't use the washer method. So, okay, so it's with experience. The more problems you do in this topic, the better you are at seeing what the best method to use is. If you've done enough problems using cylindrical shells, you can see what cylindrical shells can do for you in the answer just by looking at the problem. Looking at the picture, you can say to yourself, well, what would it look like to use cylindrical shells? Would it work? Right? You can visualize very quickly in your mind whether or not a particular method will work for you. And if you see in your head like, oh, I think this will work very easily, then you just do it. Right? Okay, but here we see that we can get the answers to this using the cylindrical shell method also. It's just a little bit harder to do with this method for this example. Okay, you get the same answer, which is good. All right, so that's another example using cylindrical shells. And it's a good method because we use cylindrical shells in the y direction, and we use dy for the integral using the cylindrical shell method. We also have to see the height as a difference of 2 functions. And so even though this is a more difficult way of doing this problem, it's very beneficial to do this problem for those 2 reasons. You're integrating with respect to y, and the height of the cylindrical shell is the difference of 2 functions of y. Okay? So this is a good example to do. You don't always do an example for the answer. In fact, usually you want to do an example to learn something from it. And so it's good to do this example if you learn something from it. Okay, let's keep going. Very good. Another example. Find the volume of the solid. Obtained by rotating the region bounded by y equals x minus x squared and y equals 0 about the line x equals 2. Find the volume of the solid obtained by rotating the region bounded by y equals x minus x squared and y equals 0 about the line x equals 2. Okay, so let's do that. So here is the x and y axis. Okay, so let me write the word solution. Solution. X, y axis. Good so far. Okay. The graph of y equals x minus x squared, it looks like this. Okay, where the points where it crosses the x-axis are 0, 0, and 1, 0. Okay, so you could easily see that, but if you plug in x equals 0, you get 0. If you plug in x equals 1, 1 minus 1 squared is 0. And so you can see the two zeros of that function very easily. So the origin and 1, 0. Now we're going to, the region bounded by y equals x, this is y equals x minus x squared, and y equals 0. That's the region that they're talking about. We're going to rotate that region about the line x equals 2. So here's the line x equals 2. We're going to rotate that about the line x equals 2. So let's give myself more space here. And so we're going to rotate that about. Okay, so you're going to take that and you're going to rotate it about the line x equals 2. Okay, so well, I'm drawing this arrow here just to note that I'm rotating about that line x equals 2. And so when you do that, let's draw a picture of the rotated region that you get from the rotation. Okay, and so now okay, so that's the rotated three-dimensional region. So we're going to find the volume of that solid. Okay, so we're going to use the cylindrical shell method again. So let's draw one such cylindrical shell we've used. So here's one of the cylindrical shells of many that would add up to the total volume. Okay, so when you're drawing these pictures, you want to draw them with confidence, right? When you're drawing these pictures on an exam or on a homework assignment where you're learning to figure it out, you might be worried that the picture might be going bad as you're writing it. As you're drawing on the piece of paper, you might say to yourself, oh no, I don't think this is working, let me stop. Just keep writing. So even if the picture gets screwed up afterwards, just keep drawing the circle you're drawing, or the vertical line, or the horizontal, right? Draw whatever you're drawing until it's done, and then see what you wrote, see what you did, and say, well, is that good or is that not good, okay? So you want to draw these pictures with confidence, okay? If you start drawing something, just draw it and see what happens after you're done. Then you put the pen or pencil away and you look at it and say, is that good? Right? Don't judge it before you're done. What I'm saying. Okay, so this looks alright. So I judge the picture after I draw it. Every time I draw a lesson, I look at it after I draw it and think whether or not it was good. So I don't worry about it while I'm drawing. I just keep drawing, okay? And whatever it is, right? So I've had a lot of practice drawing these pictures. I've drawn them a lot of times. So they've come out a lot better now than they used to. So when you first draw these pictures, it may not look good at all. And it may not, be that good. I'm not an artist myself, so I can understand trying to draw these pictures and, they're coming out really strange. But the more you draw these pictures, the more they start to look like they're supposed to look, all right? So with practice, the pictures start to look better, okay? So here is the cylindrical shell that makes up part of the entire thing, okay? And so that will help us to find the definite integral that gives us the volume. So the volume is equal to the definite integral. Now here's the cylindrical shell, right? The cylindrical shell is like this, right? And so that means that it's an integral with respect to x. And so we're integrating from 0 to 1. The x values, these cylindrical shells, this is the fixed x value, right? They range from 0 to 1. Difference from 0 to 1 of 2 pi. Now we have to modify our radius again. It's not going to be x. This time, it's going to be the distance from this point on the line x equals 2 to the point on that point there, right? This is the radius of the cylindrical shell. Okay, that's the radius of the cylindrical shell. And what the radius equals is it's 2 minus the x distance of this point on the curve, what x is on this point. Well, so it's just 2 minus x, okay? That's the x distance, x. So 2 minus x is the radius. So 2 pi times the radius, 2 minus x, 2 pi r is the circumference of the circle. So the circumference of the circle that makes up the cylindrical shell is 2 pi r. And the radius of the cylindrical shell excuse me, is 2 minus that x distance, so it's 2 minus x. Okay? So you need to know the formula. I wrote this down early on in the beginning, right? That the volume of a cylindrical shell is 2 pi r h delta x, right? Where delta x is the thickness of the cylindrical shell. R is the radius of the circle, so 2 pi r is the circumference of the circle, and h is the height, right? So you have to be able to see how you get the volume of the cylindrical shell using this formula. Because if the example is changed slightly, in certain examples, instead of r, you might need to solve for the radius of the circle, right? The radius might not be x. In the beginning it was 2 pi x, right? H delta x. But the radius is not always the x coordinate. So you have to visualize what the radius is of the circle in the picture, and then find a formula in order to express the radius of the cylinder. Okay? And sometimes the h is not always the height of a function. Sometimes we saw the h was a difference in two values of a function. And so you have to be able to see that also. Here though, the h is easy. The h is just the height of the function, right? And the height of the function is the y value, which is equal to 2x minus x squared. Okay, so some problems you need to think creatively for r. Some problems you would need to think creatively for h. And some problems you may need to think creatively for both r and h. Right? In this problem, you need to think creatively for r. R is 2 minus x. But the h is still easy. The h is just the height of that given function, x minus x squared. So in this problem, the difficult part is just the r when computing that formula, okay? So we just need to calculate this depth integral, and when we do, we found the volume of this region rotated, of this shaded region rotated about the line x equals 2. Okay, so let's calculate this depth integral. It's equal to 2 pi times the depth integral from 0 to 1 of 2x minus x squared, which is, using the FOIL method, it's 2 times x, which is 2x, minus 2x squared, minus x squared, plus x cubed dx. And so now this integrand is x cubed minus 3x squared plus 2x. Okay, so now 2 pi times that depth integral, so that's 2 pi times that. It's fine. This depth integral is an antiderivative of the integrand function, which is x to the 4th over 4 minus x cubed plus x squared. Evaluate from 0 to 1. Good. And so now, if you plug in 0 into this, you get 0. So if you do 1, plugging in 1, then this would just be plugging in 1 minus plugging in 0, which is just plugging in 1 minus 0, which is plugging in. So it's just 2 pi times plugging in 1 here. So you get 1/4 minus 1 plus 1. That's 1/4, okay? And so that's equal to pi over 2. And so the answer is pi over 2, okay? So we can make this step quicker by seeing that if you plug in 1 here, you get 1/4 minus 1 plus 1, which is 1/4. And if you plug in 0, you just get 0. So 1/4 minus 0 is 1/4. There's 2 pi times 1/4, which is pi over 2. So the final answer is that the volume of the rotated region, the volume of the shaded region rotated about the line x equals 2 is pi over 2. Okay, and so that's the answer to this example. Okay. Okay, good. Okay, so that's the end of 7.3. So let's go to the next section. Seven point four, arc length. 7.4 arc length. Okay, so in this section we're going to compute arc length. Okay, and so the question we ask is, what is the length of a curve? Right? It's a very simple question, but with not a simple answer. It sounds like it might be simple, but it isn't. So let's see, for instance, if we were to say, if we look at this curve here, right? Right? What's the length of that curve? It's not an easy question to answer, right? It's amazing how you can ask such a simple question, and yet it's very complicated, right? Just the length of that curve is an extremely complicated question. It's not a straight line, right? It's not the circumference of a circle, but that was once quite a difficult question to answer. So this is not an easy question to answer what the length of just a curve like that is, right? Intuitively, you might think, well, if I had a rope, right? I know I can measure the length of a rope, right? If it's just straightforward. If I could have a piece of rope and I could take that rope and I could line it up with the curve, right? If I had a piece of rope in real life and if I just made it fit the curve exactly and I held it, and then I took it away from the curve and I just stretched it, not forcibly stretched it, just flattened it, then I could measure the length of the flattened string, and then I would know how long the entire curve was, right? So physically, you could see how you could find a way to do something weird and maybe get the length of the curve, right? But not directly. Maybe you knew the length of something else, and then you sort of deformed it to match that, right? So if you knew the length of a string, and you kind of just deformed it to make it into this curve, they'd have the same length. And so knowing the length of just the straight line originally, you would know the length of that, okay? And so in a real life setting that might work, and even mathematically that might work. But what we're going to learn about is a method where we don't do that, okay? So the method we're going to use is going to be using definite intervals. So we're going to be able to find the length of that curve by calculating a definite interval. Okay? And so let's look at this. Let's approximate the length of this curve. And let's do it this way. Let's say we have the interval from A to B, right, what that curve is on. And let's say we split that interval into n subintervals. Okay, we're going to split that up into n subintervals. Then on those n subintervals, I'm going to take the points on the graph, on the curve, that are right above the endpoints of each subinterval. Okay? So what I get is a sequence of points on the curve. Now let's connect each next point with a line segment. And so now we're going to get a bunch of line segments where each line segment connects one point on the curve to another next point on the curve. Okay? And so what I can say is that if I add up the lengths of these n line segments, that would be an approximation to the length of the curve. Make sense? Okay? So I just took the interval from A to B and I subdivided it into n equally spaced subintervals. Then I took the n points of each subinterval and I found the point on the curve with x values, the n points, the subintervals. Then I took those points in the curve and I just connected them with line segments. Now, the sum of the lengths of those line segments is an approximation to the length of that curve, right? So you can see that. Now, if we took n and we took the limit as n approaches infinity, where instead of a finite number n of subintervals, we took n to go to infinity with infinitely many subintervals, then by adding the lengths of infinitely many line segments that connect to two adjacent points in the curve, two close nearby points in the curve, and we took the sum of infinitely many of those line segments, we would be approaching the actual length of the curve. Okay? And so that is the idea of the method we're doing here. Okay? And so here, capital L, which is the actual length of that curve, is going to be equal to the limit as n approaches infinity of the sum from I equals 1 to n of the length of p sub I minus 1 p sub I. And what is that? P sub I minus 1 p sub I is just, let's say this is p naught, this is p1, that's p2, that's p3, that's p4, dot dot dot, p sub n minus 1. These are the points on the curve, right, with the endpoints of the subinterval. Then p sub I minus 1 p sub I, the absolute value of p sub I minus 1 p sub I is the length of one of these line segments, right? So this symbol here is equal to the length of the line segment connecting points p sub I minus 1 and p sub I on the curve. Okay, so this symbol is the length of the line segment connecting p sub I minus 1 and p sub I on the curve. So for instance, the length of this first line segment from p naught to p1, the length of that line segment would be absolute value of p naught p1. Absolute value of p naught p1 would be the length of the line segment connecting the point p naught to p1, both those points on the curve. Okay, so this sum is just adding up the lengths of all of the line segments there. Okay, and then the limit is just taking the limit as we consider infinitely many subintervals of equal length and the sum of the infinitely many line segments we get from those infinitely many subintervals. So capital L is equal to the limit of that. Okay, and so this can all be formulated, but we're going to skip some of the formulation. Okay, we're actually I'll spend a little time. Okay, so when f is when f has a continuous derivative, f is smooth, because a small change in x produces a small change in f prime of x, we can derive an integral. So when f has a continuous derivative, we can derive an integral formula for L. Okay, so when f has a continuous derivative, we can derive an integral formula for L. Okay, and so we're going to derive that formula now. So that's my introduction. I'm going to write on the next board the derivation, okay? And so we're going to assume our function f has a continuous derivative, meaning f prime is continuous. And we're going to derive the integral formula for L from that assumption. Okay, let delta y sub I equal to y sub I minus y sub I minus 1. Then the length of p sub I minus 1, p sub I, is equal to the square root of x sub I minus x sub I minus 1 squared plus y sub I minus y sub I minus 1 squared, which is equal to the square root of delta x squared plus delta y squared. Okay, so just to illustrate this one part, right, you have your curve, right? You have the point P naught and P1. And if you want to know the length of the line segment connecting those 2 points, right, by the Pythagorean theorem, you would know that the length would be the square root of this squared plus this squared. This squared, well, this is x1 and this is x naught. Then the length of this side is x1 minus x naught. And if this is y naught and this is y1, then this length is y1 minus y naught. And so the length of the hypotenuse, or the length of the line segment connecting P naught to P1, is the square root of x1 minus x naught squared plus y1 minus y naught squared. Okay? That's for P naught and P1. If we just change this from P naught to P1 to P sub I minus 1 to P sub I, then the difference in x values would be, this would be x sub I minus 1, this would be x sub I. This would be y sub I minus 1 and y sub I. So the difference in x values would be x sub I minus x sub I minus 1. This would be y sub I minus y sub I minus 1. And then the length of hypotenuse would be the square root of this squared plus that squared. And then you get x sub I minus x sub I minus 1 squared plus y sub I minus y sub I minus 1 squared. The square root of that sum, the squares. That would be the length hypotenuse right by Pythagorean theorem. And so that's how we're getting the length of p sub I minus 1 p sub I is the square root of that. And that's equal to delta x squared plus delta y squared. Where this is delta x, and that's delta y. Right? Now, this is the square root of delta x squared plus delta y squared, again by the Pythagorean theorem. This is the delta x, and then you square it, and then that's delta y, and you square that. Right? By the mean value theorem, on x sub I minus 1 comma x sub I, there is a number x sub I star such that f of x sub I minus f of x sub I minus 1 is equal to f prime of x sub I star times x sub I minus x sub I minus 1. Okay, so by the mean value theorem on that interval, there is a number x sub I star such that the difference in y values is equal to the derivative at that point times the difference in x values. What does that mean? So if you have the x-axis and y-axis and you have your curve, you have x sub I minus 1 and x sub I, right? That's your delta x. You have the point p sub I minus 1 on the curve and the point p sub I on the curve. We have a sequence of points, and these are the 2 consecutive points in that sequence. By the mean value theorem, because this function y equals f of x is continuous on that closed interval, that means that there is some number x sub I star such that, so if you take this line segment connecting p sub I minus 1 p sub I, that line has a slope. And that slope is the change in y over the change in x, right? That's the slope of the line. Well, the change in y, the delta y here, is equal to the value at p sub I, which is f of x sub I, minus the height of the function p sub I minus 1, which is f of x sub I minus 1. That's the difference in f values. That's delta y. delta x here is equal to the difference in x values, which is x sub I minus x sub I minus 1. And so the slope of the line is delta y over delta x, right? And so delta y over delta x here would be equal to f of x sub I minus f of x sub I minus 1 over x sub I minus x sub I minus 1. Okay, so delta y over delta x is equal to this difference over that difference. And so that's the slope. Okay, and so the mean value theorem says that there's some point on the curve, call it x sub I star, because it's a point in the ith subinterval. The subinterval from x sub I minus 1 to x sub I is the ith subinterval. X sub naught to x sub 1 is the first subinterval. X sub 1 to x sub 2 is the second subinterval. X sub 2 to x sub 3 is the third subinterval. X sub I minus 1 to x sub I is the ith subinterval. Okay? And x sub I star is just some point we choose in the ith subinterval. So that's what x sub I star is. It's a point we choose in the ith subinterval. The mean value theorem says that given this situation, the slope of this line segment connecting those 2 points, which is this divided by this, right? The slope of that line, which is the slope of that line segment, m. There's some point you can choose in this there's some point you can choose here, so that the derivative, so that the slope of the tangent line to the graph at that point above that x value, the slope of that is the same as the slope of that. Or in other words, there's some point we can choose here where f prime of x sub I star is equal to the slope of the line segment connecting those 2 points. Okay, so the mean value theorem tells us that this is equal to f of x sub I star for some x sub I star in that interval. And so saying this over this is equal to this is the same as saying that this difference is equal to this times x sub I minus x sub I minus 1. Okay, and so that's the conclusion of the mean value theorem. And so all of this is explaining what that means, how we get that. Okay? Or delta y sub I is equal to f prime of x sub I star delta x. Right? Delta y sub I is this, equals f prime of x sub I star times, and that's delta x. Or you could write the same equation using that. So we reached this conclusion by the mean value theorem, and we could rewrite the same equation as that equation. Okay? And so now we're going to erase all of this, because that was to explain that one statement there. But that's just explaining the mean value theorem. It's not explaining this new material. Okay. Therefore, the length of p sub I minus 1, p sub I, is equal to the square root of delta x squared plus delta y squared, which we showed before. So right from this, okay? And that's equal to, that's repeating this, this is equal to the square root of delta x squared plus now the delta y here is the delta y sub I here, because it's for these 2 points, and that's this. And so you can replace the delta y here that's being squared with that. So instead you can square f prime of x sub I star delta x. You can square that instead. Okay? And so this is equal to the square roots, factoring out the delta x squared. It's the square root of, well, I'm about to put in times the square root of delta x squared. And in here, you put 1 plus f prime of x sub I star squared. Okay? And so now that's equal to the square root of 1 plus f prime of x sub I star squared, and then the square root of delta x squared is delta x. That becomes delta x. Okay, so what that implies is that capital L, the actual length, is equal to the limit as n approaches infinity of the sum from I equals 1 to n of the length of p sub I minus 1 p sub I. And that's equal to the limit as n approaches infinity of, well, what we showed is that the length of p sub I minus 1 p sub I is equal to that. And so I'm just going to substitute that part of the expression. So sum from I equals 1 to n of now that the square root of 1 plus f of x sub I star, f prime of x sub I star squared delta x. Okay, so we have now is that L, capital L, the actual length, is equal to this limit. Okay, and so from that, I'm going to erase this here and this, erase everything up here. And so from knowing that capital L is equal to that limit, our conclusion, knowing the definition of the definite integral, the conclusion is that the actual length is equal to the definite integral from a to b of the square roots of 1 plus f prime of x sub I of x, f prime of x squared dx. Okay, this integral exists because g of x, which is equals to the square root of 1 plus f prime of x squared, is continuous. And that means it's continuous on the closed interval a comma b, which means it's integrable. We said before, if you have a continuous function on an interval, then that function is integrable on that interval. So this function, that integral exists. Okay? So our conclusion is that the actual length of that curve is equal to definite integral from a to b of the square root of 1 plus f prime x squared dx. Okay, and so that is our conclusion. We got it from this capital L being equal to that limit. Okay, and so now I'm going to write down the arc length formula from that. For that conclusion, I'm just going to state that conclusion as a theorem. Okay, so the theorem is this. The theorem is the arc length formula. Okay, if f prime is continuous, on the finite closed interval a comma b, which is our assumption before, then the length of the curve y equals f of x, where a is less or equal to x, less or equal to b, is capital L is equal to the definite integral from a to b of the square root of 1 plus f prime of x squared dx, or capital L is equal to the definite integral from a to b of the square root of 1 plus dy dx squared dx. Okay, so here we have the arc length formula theorem. If f prime is continuous on the finite closed interval a comma b, then the length of the curve y equals f of x from a less than x less than b is equal to this or that. And the only difference is instead of writing f prime of x, I write it using this notation, dy dx. And so f prime of x squared becomes dy dx squared in the expression. Okay, and so now we use this formula in order to calculate the length of an arc. Okay, and so next class we will use the arc length formula to calculate the length of a curve. Okay? All right, so I'll see you next time.